All right, so next up we have Suman Banerjee talking about wireless interference.
Okay. Good morning, everyone. My name is Suman Banerjee. I'm a faculty member in computer science at the University of Wisconsin. And it's a pleasure to be here to tell you about some of the work we have been doing in trying to understand wireless interference. So the group that I head in Wisconsin, it's called the WINGS Lab, and a lot of this work is, of course, done by a lot of my students. And so I wanted to share some of the stories we have had. So before we do that, I do realize that I stand between you and lunch, although I know there is another short talk. But as a gentleman from Arizona State University pointed out, I should be lucky that actually I'm not between you and beer, which probably is worse. So with that, let's talk about wireless interference. So as we all know, when we use wireless systems, we expect, or users expect, wire-like performance. And the real experience that people have is that, it seems, if you think of at home, it seems to work somewhat effectively. It's flaky sometimes. Connections do drop. And when we looked at our university, and I have a couple of colleagues from our university who can vouch for this, students complain, is anybody else finding this network to be slow and flaky? And then there's a response which says, I want to figure out what I should do to fix this problem. And one of the responses that came back, as you can imagine, says, yeah, just restart the laptop. That seems to solve the problem, right? So it's unfortunate. And the problem is really hard for administrators. And in our case, this was a specific example in our department where our administrators came and, of course, said, we heard about the problem. When we came, the problem had disappeared. We could not reproduce it on demand, so we couldn't even figure out what was wrong. So really, as we all know, the issues that we experience are transient. And obviously, we lack sometimes enough details and tools to debug this problem. So that's sort of what I'm trying to address in this work. So really, the core question we want to understand is my wireless network operating well enough? Right, and how do I measure that? Again, at home, this is actually getting quite important. You don't want to be watching movies and having this problem of the network buffering, especially if you're watching it on an iPad or other device. It can be quite frustrating. Why should this audience care? And I'm sure a lot of you know this. There's obviously going to be an increasing delivery of all content over wireless mechanisms, even in homes. Media delivery, Comcast talking about Xfinity apps on tablets and other handheld devices. And essentially, anecdotally, I keep hearing that a lot of the operators get calls from the customer saying, oh, my wireless is not working. And really, the operator had nothing to do with the wireless, but they have to handle it, right? So it's really become an important thing for operators to understand how the Wi-Fi or the wireless experience is and how they can help customers to debug problems when they occur. So this was a very nice graphic published in the Wall Street Journal. So it's a little bit probably oversimplifying the problem. But they called it the drain of Wi-Fi bandwidth. And the point that was being made in this graphic was, imagine that today, operators are talking about bringing even 300 plus megabits per second into the home. That's the wired bandwidth that's coming into your home. But due to interference, whether it's from various Wi-Fi sources or various non-Wi-Fi sources, maybe a microwave oven, maybe an analog phone or a Bluetooth headset, that bandwidth gets diluted. And then by the time it hits your device, it's down because it's shared. It's down to a few megabits per second. So obviously, it sounds, we want to say, yeah, we get 3 megabits per second to my home. But if you want to watch a Netflix movie and it requires a significant bandwidth, sometimes it cannot be supported because of all the interference. So the problem that we wanted to study is essentially providing some form of a real-time diagnostics toolkit for the network. And we have been trying to look at how can we provide a real-time dial that gives you a score that says, yeah, your network's at 90 out of 100. And if it's low, it should be able to tell you what are the causes, what are the root causes for this. So as an example, imagine you have, this is an example from an enterprise, but you can imagine this to be in your home as well. where you have a bunch of access points and client links. And what we want to do is, let's say a particular set of links are performing poorly. So on the x-axis, you have the goodness. On the y-axis, you have the different links. Say link L1 is performing poorly. I want to be able to say that this is caused by that security camera over there, and the impact on the performance of the link is 0.7. And the link 2 may be impacted by 2 devices, a microwave oven and a cordless phone with some different impact. So I want to be able to classify all these things. So that's sort of what we have been trying to do. So I want to basically talk today about RF interference debugging. That's sort of the approach, the focus we have. And then we have deployed this solutions that we have developed on a couple of environments in Madison, Wisconsin. And I want to talk about that, and then talk a little bit about potential open standards. And I know this communities also, or related communities are thinking about that today. Okay, so let me talk about RF interference debugging. So we've done a lot of work in this space. We started out by doing this very simple problem, which I call post-mortem of a Wi-Fi packet. So imagine that a Wi-Fi packet was transmitted over the air, and it was lost, that the receiver could not decode it. Is there a way we can tell what happened? Why did that packet get lost, right? So it's a post-mortem because we are looking at the packet after it failed and then saying, why did it fail? And so what we were able to do was basically look at bit patterns in the signal, bit patterns in the packet. So imagine that a packet is lost. That means the checksum failed. But by looking at the bit patterns of the failed packet, you can still predict, or at least infer, whether it was lost due to collision from other packets, or it was lost due to a weak signal. That means you're very far away from the access point, and therefore it was lost. So we did this work in 2008. That was really the genesis of this whole investigation. And then we looked into sort of two halves, looking at sources of interference, whether the interference is from other Wi-Fi sources, or it is from other non-Wi-Fi sources. So we have a body of work, and I have some references to papers that we have published in the literature. But today I want to focus on the non-Wi-Fi interference sources because it's a little bit unique from a lot of the work that has appeared in literature, and also we have developed some tools that I want to talk about. So I'll talk about these two techniques that we have developed. One's called AirShark and one's called WiFiNet. So let's talk about non-Wi-Fi interference. As we all know, there are lots of non-Wi-Fi devices all around us. We kind of classify them into different types. There are narrowband devices. Basically, they emit energy in a very narrow band. Broadband devices like microwave, they're obviously not communicating devices, but they emit energy that cause interference. And then there are all these frequency hopping devices all around us. Of course, if you take a spectrum analyzer and walk around, you will see activity. Here in the picture, I have shown what happens for the 2.4 gigahertz spectrum. Now, looking at the picture, you can't tell there's a frequency hopping phone or a microwave oven. We have done some analysis and figured it out. But some of these devices actually operate at pretty high signal strengths that can cause significant interference to Wi-Fi devices. So is this a real problem? So we have looked at performance of these performance of Wi-Fi in presence of non-Wi-Fi devices. And what this plot actually shows is essentially as the non-Wi-Fi interferer signal strength goes up, what is the impact on throughput? And in this case, we are plotting UDP throughput. TCP will, of course, suffer more because it also tends to back off in a certain way. And we found that a lot of devices like, let's say, a video camera, this is security cameras, or analog phone, sometimes microwave ovens, can basically bring your throughput down to almost zero, right? So this is actually a significant issue, and we have seen this over many different experiments. Obviously, the interference problem is higher when the devices are closer to you and less when they're farther away. So the first tool that we built is called AirShark. Obviously, the name plays on Wireshark, and this is really analyzing over-the-air activity on the RF medium. And this is actually a software-only solution for detecting non-Wi-Fi devices using commodity Wi-Fi cards. So I'm not actually embedding a specialized spectrum analyzer. This is a single-node system, works in real time, and can also work when there are simultaneous non-Wi-Fi devices operating in the air. So what we did was, this actually right now has been implemented using the Atheros chipsets, so the Atheros AR9200 series and 9300 series actually. And the capability that we use is what Atheros exposes today. It exposes the signal strength information for every OFDM subcarrier of a Wi-Fi channel. So essentially, a Wi-Fi channel, let's say, has about 50 or 60 subcarriers. you can get a sample of energy or the receive signal energy per subcarrier. So you essentially have these samples which we call power per subcarrier, and that essentially serves for us a very, very coarse-grained spectrum analyzer. We wanted to do this using a Wi-Fi card because we want every device, your laptop, your mobile device, mobile phone, tablet, to behave like a spectrum analyzer, and we should be able to use it as a tool to diagnose things, as opposed to carrying extra spectrum analyzer hardware around to go and debug problems. So this is what we want to do. We also want to embed this into access points. We want to embed this into client devices so that they can take into account this information and then do something, react somehow to it. So that would be a very powerful concept, right? So the challenge that we had to solve is that in some sense, a Wi-Fi device was obviously not meant to be a spectrum analyzer. It's a very, very coarse-grained spectrum analyzer. So the picture here essentially shows that you have, in frequency, you have these OFDM subcarriers. You have these bins where you have some observations you can collect. Each bin is a subcarrier, so it's about 312 kilohertz. And then you have a certain frequency in which you can observe, time frequency, you can observe these samples. Roughly, we can get about 1,000 to 10,000 samples a second. And then, so this is fairly coarse-grained. And then we have to build sort of models out of this information to figure out what type of device is operating over the air. Okay? So the other thing that we had to do was a lot of these non-Wi-Fi devices are obviously going to sweep across the entire 2.4 gigahertz band. So your Wi-Fi device, which is operating on a particular channel, is not going to be able to see everything. So we have to essentially sweep the channel in some order and hopefully see enough to be able to infer what device is operating. Right? So we kind of have an approach where we first do some sort of continuous spectral sampling by sweeping the channel in some coarse-grained manner over different Wi-Fi channels. And then in each channel, we are observing this power per subcarrier, and we want to build models. So we first do this sweep operation, which is happening continuously in the background. Then we define pulses. We basically try to identify signatures of different devices. For that, we need to know what are interesting events. So we have something called pulses, which are essentially significant energy observations in certain frequencies that we can observe. And then we have a whole slew of techniques to extract features. The features are the key components that tell us what device is operating. So, frequency hopping device has a certain pattern that you can imagine. Microwaves have some other pattern. So we basically extract these features, and from that, finally, we build a classifier system that tells us what exactly the device type is. So that's sort of the idea of the system. This is a very standard machine learning approach that a lot of systems have used worldwide in various kinds of applications. We use this, but using a Wi-Fi card as a source of data to identify these different devices. So instead of going into specifics of those classifiers, there are papers that describe it. I kind of wanted to give you a sense of accuracy of this system. So the way to think of AirShark is that it is in a minimal way, if you're familiar with this product called WiSpy, which is sold by this company called MetaGeek. It's a very useful tool. They actually build some extra hardware which operates in the USB form factor, and you can actually look at some spectrum properties. AirShark essentially is a tool that gives you that as the first step using a Wi-Fi card. It gives you the spectrum behavior, and on top of that, it gives you ability to analyze what type of device is actually operating. So we did this classification, and we basically do have pretty good accuracy for the most part. A lot of devices we can accurately determine, especially when they're at least at minus 80 dBm or higher, which is, if it's very low, I guess the accuracy is bad, but then perhaps you don't care as much about that device at that point. This is when so these are under controlled experiments. So this is, we turned on a device, we knew what we turned on, and we tested to see if we can detect the device. Of course, there's a training phase. So of course, you have to learn the features of each device type. So there is a labor-intensive part to it, but that's sort of unavoidable. This we've seen about 98% accuracy for the most part when the signal strength is at least 80 dBm. The other interesting question is when there are multiple devices operating. So imagine that you have a Wi-Fi, you have a microwave oven and a Bluetooth device and something else all operating at the same time. Can we detect things and tell them apart? And turns out, even there, obviously your accuracy is going to go down because you're going to confuse different kind of pulses that are showing up. But we have still been able to do quite well. So we can actually tell apart these multiple devices that are operating simultaneously. we got some nice, so when this paper first came out, we got this interesting comment in Slashdot. There were many, but one of them said, honey, did you leave the microwave on? And the response was, dear, let me log into my PC and check, because now my Wi-Fi device can actually figure out if the microwave is actually running. Anyway, so that was AirShark. Then the next tool we built is what we call WiFiNet. And here, so the first step was to identify what is in the air. And the second step then is, knowing that I have this device in the air, can I tell how much interference is that device causing my Wi-Fi link? Right? So we call this WiFiNet, and we essentially try to quantify the impact that each device has on a Wi-Fi link. And the idea of this is very simple and intuitive, I think. So imagine that there is a Wi-Fi link from an access point to a client that's sending some packets, that is sort of these gray-colored rectangles that you see. These are the packets going on the air. And then this analog phone is emitting what we call pulses. These, we of course don't know, by looking at a pulse you don't know, but we have a signature, so that tell us this pulse belongs to an analog phone. And we have pulses coming from these analog phones. What we try to do is we try to correlate that every time if a packet is sent and a pulse is sent from an analog phone at the same identical time and there is overlap, it leads to a loss for the packet. Right? Then we can assign a blame to that particular analog phone, saying, you are probably causing this packet losses. If it doesn't happen consistently, you assign a partial blame, possibly, or no blame, right? So that's sort of the idea. We look at overlap patterns between non-Wi-Fi activity and Wi-Fi activity, and then can conclude who is causing which problem. So if every time there is an overlap, there is loss, we say impact is 1, and then we have a probabilistic way of kind of interpolating. Okay? Now, there was an additional thing that we had to fix to implement WiFiNet. Okay? And that is, you need to be able to tell apart devices of the same type. Let's say there are two cordless phones. They will all look the same. And if I do not know that these pulses belong to cordless phone 1 and these belong to cordless phone 2, I may misrepresent the blame to one device. So we had to do some tricks to kind of figure them out and separate them out. Right? And you can do that by looking at some timing and frequency properties of the pulses and can infer this. So, so that was the idea of trying to quantify impact. Now, as a continued part of this, once you are able to do this sort of separation of pulses into devices, essentially it's like establishing identity. Right? For a Wi-Fi card, you see pulses in the air from non-Wi-Fi devices. You don't know who is sending those pulses. There's no MAC address, so there's no identity. But once you establish identity, which is what WiFiNet actually did, then you can do very interesting things. You can do localization, because essentially I have pulses which have signal strength information, and I have figured out unique identity for each pulse. Now I can do localization. I can essentially come up with techniques to tell me where these devices are. And we've come up with some models that are sort of related to how Wi-Fi localization works, but the key new thing that we did was assign identity to these pulses that are from non-Wi-Fi sources. So we built some probabilistic models. Essentially, the pictures show that we have multiple observers that have to observe the same pulse, and every pair of observers think that the device is in a certain region. And the dark black spot essentially is the most likely location that the device is. And by overlapping multiple such observations, we can really narrow it down to a very precise location. And it turns out, again, these are based on experiments in one particular environment, so you should never take this as going to hold everywhere forever. But at least with 6 to 7 observers in a reasonable sized building, you get pretty good accuracy of up to 4 meters error in the median case. Okay? Of course, it will vary based on lots of parameters, so I wouldn't go into too much of the exact number. Then the other result to point out is that we are also able to accurately assign blame. So what we did was we transmitted data on a Wi-Fi link. Let's say you got 10 megabits per second. Then we turned on a non-Wi-Fi device, and we get 4 megabits per second. So we know exactly that we sent 10 in the first time and 4 in the second time, so the impact is, let's say, 0.6. And with our system, with WiFiNet, we wanted to check, by looking at this pulse overlaps, can we come up with the same number, right? So the plot on the left essentially shows that our system's pretty accurate, so the ground truth is because we know what we were doing exactly, and WiFiNet's estimate was very similar. So if it's perfect, x-axis is ground truth, y-axis is their estimate, everything should be on the 45-degree line. We are fairly close, which is a good thing. And the y-axis, the right side plot is essentially the same data, just plotting the error in estimate instead of showing the same data on both axes. Similar results for multiple devices operating simultaneously. So this is all what we implemented. So to give you a sense of what this whole toolkit is going to provide, there are two parts. There is AirShark that tells you what devices are in the air. So if you implement this in an access point, then access point 1 might say, oh, I know there is a microwave oven. Access point 3 may say, I see a video camera. Access point 2 may say, I see a microwave oven and a video camera. WiFiNet will then take all the data and say, yes, let's say the video camera has an impact of 0.4 on link L3, and it can also say that the microwave oven is on this corner, the video camera is on the other corner. So that's sort of the overall system that we've developed. The thing to remember is that AirShark is a single observer system. So I can just put it on my tablet or my one single AP, and it will just give you this information, while WiFiNet requires multiple observers to collaborate to be able to collect this data. Okay. So we have since then been trying to kind of push this work a little further. We have been talking to Aruba a little bit and have been trying to implement AirShark on the Aruba access points with some success. And we are trying to, the plan is to pilot this on our campus because it turns out that we have a lot of Aruba APs on our campus. And we want to use this to kind of do some diagnostics on our campus. We are also releasing an open source version of the driver with the help from Qualcomm Atheros. I think there is a version that's already out, and we are actually releasing this from our website as well very, very soon for these two chipsets, the Wi-Fi chipsets. We have also built some standalone client tools. So for Samsung Nexus, so you have to, of course, root the device. But for Samsung Nexus, we just released this on October 2nd, so a few days back. We call this new version of the tool, we have a new name. Instead of AirShark, we are now calling it WiSense. Doesn't matter, really. And there's a website, wisense.io. You can at least go there, and there's instructions on how to access the content, how to access the driver and install this app. You have to, again, root the phone. Now, the only limitation, though, I have to admit, is that right now we only work with Atheros. And so the Samsung Nexus actually don't have a built-in Wi-Fi Atheros chipset. So we recommend you get a USB-based Atheros Wi-Fi card, which you hook into the Samsung device, and you can actually use it. Okay? So you have to unlock the phone, update the driver, and the app is in Google Play. You can download it. So what I'm going to do is show you a very quick demo of this system. And for some reason, for this demo, I have to minimize. I can't do it in the full screen mode, but hopefully this will give you a sense, and I'll walk you through it a little bit. So this is the Samsung device. You can see the antenna on the side, which is connected. That is the Wi-Fi Atheros chipset. This looks, in some sense, a lot like WiSpy. So there are basic things, like this screen basically shows all the ESSIDs of devices. That's, of course, a very trivial capability. Then we have heat map. So this is actually taking the spectrum sampling information and projecting the information on screen. So obviously, green is very low signal strength, red is high signal strength. And it only picks up the non-Wi-Fi activity. So if there's a Wi-Fi activity in air, that is filtered out. So right now, for example, I believe analog phone might have been started. And you see the yellow thing is essentially the analog phone. This is showing in the spectral heat map. But then the system will also analyze this data and will actually predict it. So the fact, this is sort of a event screen where the yellow line essentially represents the analog phone is running, and it plots the signal strength at which the analog phone is detected. And there's a device view and all that. I'm going to forward this video a little bit to show you some of the interesting parts. I think later on a microwave oven will be started. So analog phone gets turned off over there. Let's see, a microwave oven will get started in a bit. I think this is showing that once you turn it off, it shows the device in a previous device pane as opposed to, or an inactive device as opposed to an active device, but it remembers that there was an inactive device. And then we will start a microwave oven in a bit. Yeah, so microwave oven gets started. It actually spreads energy over a much wider band, usually on channel 11 of the 2.4 gigahertz spectrum. And then this will be detected. by your system, and it will show in the event pane that the blue thing that you see sort of there at the bottom, that is the microwave oven detected. The yellow was the previous analog phone that was earlier in time that is still sort of shown in the timeline that you observe. And then sort of towards the end, I'm going to just forward this. We are going to have multiple devices running simultaneously. There's turning on a microwave oven. I think yeah. So here you will be able to see there is 3 lines that will show up. There's a yellow one, which is a Bluetooth device. The blue, in this case, is an analog phone. There's a legend below, which is very hard to read from perhaps the back of the room. And red is the microwave oven. And we are essentially trying to separate all of them and their signal strengths as they are observed as being active. Okay? So this is essentially the tool that we have finished. I'm sure it'll have kinks. Now, the only thing that I'll mention about the tool is if you go to the web page, you'll see this. The tool, when you download and install it, we have a default of it. The device will send spectrum sample data to us in our server in Wisconsin, completely anonymized. We are not tracking you or doing anything bad. Of course, you can turn it off. It's optional. But we hope that as a service to the community to give you a tool that can give you this capability, if you are willing to share physical layer spectrum data with us, I think it'll be an interesting study to see globally what kind of activities are observed across 2.4 band, or actually it can be made to work in 5 gigahertz band also, but you can get some fine-grained physical layer data in a very, very easy way, and we would love to collect that data and report it in other papers in the future. Okay, so I'll continue with the talk. So we got a lot of press a while back, so we are very grateful for that, and we do want people to be able to use this and give us some feedback on how this is working. Now, let me jump ahead a little bit and talk about some of the deployment experience. So these are the tools we have built. So we went and we ported all this. One you saw was the tablet version. So it runs on a Samsung Nexus. You have to customize a little bit. The other version is actually ported to OpenWRT, which are open source access points. And we are running them on this very low-end platform on a Geode processor, 500 megahertz processor, 256 megabytes of RAM. We equip these access points with dual Wi-Fi cards just because we want the redundancy for some analysis. But really, it's a regular access point that we operate. We have deployed this in over 30 homes in Madison. And more recently in a couple of enterprise environments. Tony's organization has a few of these right now in their office, just deployed last week. And we have a controller that's hosting this service. And there's actually a lot of data that's coming in as a result. So just to give you a sense, these are in people's homes. So they're probably obviously a lot of traffic goes through it. Some of these access points basically see about 5 to 10 gigabytes of data per day. So it's pretty normal. One of these is my home. So these 2 buildings, building 1 and building 2, are actually large multi-dwelling apartments. And so there's a lot of these access points in very, very dense interfered environment. Whereas the ones which are labeled others are sort of single-family homes far out in less busy areas. One of them is my home, and I think I'm not a very high user of data from my home. But the more interesting ones are the 2 large multi-dwelling buildings. One of the things, so we have done this study for a while. These are just some snapshots of information. There's a lot more. We have published some papers, and if you send me email, I'll be happy to point them to you, or if you go to my webpage, you can get some of them. But one of the things we have seen is that, especially in the multi-dwelling buildings, sometimes the channel utilization is pretty high. So the dotted line is 50% channel utilization. And we see routinely more than 50% channel utilization. You may think 50% is not that bad. Actually, it's pretty bad because a lot of small things can cause a lot of interference after you hit that point. And of course, this data that you see is for each AP, and it's really averaged. But if you look at individual days, there are days when it's close to 70 to 80%. And that's really at a point where users may find a lot of issues, performance issues that are going on in this environment. We have done long-term performance studies. One of the things we did was we came up with some metrics to sort of predict performance. So this is 2 different access points that are shown. This is over a period of few months, I think. There is a period here. So this value that is plotted here, we call it WIT, W-I-T-T. It stands for Wi-Fi-based TCP throughput. So it's basically a way, using the data we observe, we try to predict if a user were to start a TCP session right now, what kind of throughput would the user expect? Now, of course, it depends on where you're going, which server you're hitting. So this is only predicting the throughput going essentially from the client to the access point or a server right close to the access point. So it's not capturing the wired aspect, right? So it's predicting that number. Sorry about that. And you can see that these two access points, it varies between 8 and I would say 16, but it goes up and down. During the winter break, it was pretty good because nobody was there. But during the semester, the numbers tend to be low. In the less than 10, sometimes 8 or 7 is the throughput. And this is for an individual client. If we assume that a lot of users simultaneously started, this number would be even lower. And so there are consistent, and again, these are averages over individual days. Again, if you take short amounts of time, there are bursts of time where the throughput goes below a megabit per second, which is terrible for experience when you're trying to watch a movie or something like that. Okay. So then we tried to understand what are the causes of poor performance. Right? So we kind of classified performance into certain categories. We said, okay, above 16, this is totally arbitrary. I think we said above 16 was very good, and then good. And I think poor was below 4 megabits per second, and very poor is less than a megabit per second, right? I mean, this is 11G and 11N, so you should be able to get a lot higher throughputs than that. And we find that in these two multi-dwelling buildings, there is a lot of cases, very poor performance happens. So 61% of the time, very poor performance happens when this column says Y, which means the loss rate coming from collisions actually have gone up quite a bit, right? That means there's a lot of collisions between multiple clients, Wi-Fi clients in close proximity. And in another case, so this is the case for building 1. We see that a lot in building 1. So obviously, it depends on the environment and the building. In case of building 2, one of the dominating factors we have seen, even though these all three say Y, it says that the signal strength, so the clients are actually very far from the APs. It turns out that in building 2, that these are sort of infrastructure APs. So what we did in the two buildings, building 1, we gave the APs away to free to end users. So they could just come and pick up one and put it in their home. So they're fairly close to the AP. In building 2, we worked with the building manager, and they deployed it in the ceiling. So obviously, it's in outside corridors, inside ceilings, and sometimes maybe in the apartment, they're a little bit far. The signal strengths are weaker, and that's causing a lot of problems in that building, and they had lots of complaints about it. So we have some tools, and we can analyze this performance as a result of this. We also classified what is the total amount of contention experienced in a particular day for each AP, and we see that we were trying to almost kind of think of, we talk about for wired networks and for co-location centers and IXPs, how many nines is your performance? So we were trying to think of how many nines is the Wi-Fi experience. We didn't come up with a precise number, but I can tell you roughly it's somewhere between 95% or less, right? So it's not even 1 9. But we see that an AP typically, if I think of very poor as really an outage, right? Because if you wanted to watch a movie, perhaps you cannot do a good quality stream. You would get per day average, say 10 minutes or more of outage, by the definition of outage being at least a megabit per second or less throughput. So there is each AP on an average day has about 10 minutes of outage by our definition of outage. And then if you count the number of days with at least 5 minutes of outage, over a period of, I think it's about 40 days. A lot of APs have, these days, 10 days, this is about 20 days where they have at least 5 minutes of outage. That's pretty bad for, if you're trying to depend on a service and trying to use it in a consistent manner, right? So this is sort of some of the experience we have seen. And we talked a lot about non-Wi-Fi performance, so I wanted to share one chart about microwaves and their impact on performance. Microwaves actually do cut throughput, right? So the blue line here is, by the way, these charts, this is the different APs, this is the airtime utilization, and you will see the middle, this horizontal line is the average, These are, I believe, the 95th and the 5th percentile, the box, and the ends are the min and the max. So microwaves essentially cut airtime or saturate the airtime by about 50%. So it goes from 0.4 to 0.6. And there is a corresponding impact on throughput for Wi-Fi devices when there is a microwave on versus when it's not on. So we have seen that in a very consistent way. Another interesting thing, and perhaps this is not a surprise to this community, we've given these access points away to people for free for them to use. And we know that some of them experience lots of problems. In spite of that, even after, I don't know, 15 years since or 16 years since the Wi-Fi standard has come into existence, very few people actually go and reconfigure the channels, right? That simple thing could probably fix a lot of problems. So our APs can see other APs too. It's not just our own APs. But over the aggregate, we see that about 56% of people never change the channel over the entire duration of the study, and 20% changed it once. Right? So it means that we probably could do better. Some people are smarter, but not most of the people. So that brings me to the next thing, which is something we are trying to explore a lot more in our work, improving manageability at large scale through some sort of cloud-based service and by using some open standards. And we are trying to implement this system, we call it Centaur, and the idea is that we want to essentially have a well-defined API for each access point, whether it's a cable gateway, whether it's a home AP. Enterprises, of course, have proprietary APIs in some cases, but we want an open API so that they can expose some interesting data which we are collecting to do this analytics and send spectrum observations to this central control where we can do some analysis and then we can come up with even interference mitigation strategies and feed it back to these APs for doing even simple things, assigning channels properly, setting transmit powers right. There are techniques we have developed where we can tweak some of the back-off mechanisms in the access points. And these are very simple to implement as such, but you have to know what exactly to do based on what else is going on around you. So we are really interested in this ability. We are starting to work on this, and we have defined a draft management API for this. We call it COPE. We call it the Common Open Access Point Platform, so we call it COPE, and it really tries to cope with all the wireless interference. We really want APs to be software manageable and reconfigurable. I was yesterday at the Open Networking Foundation in a meeting, and I'm trying to see what are the mechanisms that we could do, we could introduce perhaps as part of OpenFlow or in some other complementary way that can enable this sort of almost a software-defined networking for home APs or home wireless infrastructure. So that's something that I'm very interested in, and I'm sure it matters to a lot of you in the audience, and we would love to talk much more about this. So that's all I had, and I'll be more than happy to take questions.
It satisfied all your curiosity. One question.
Forgive me if this is on the previous slide and I'm just not remembering it, but the source of interference you focused on were wireless telephones, analog telephones, and microwaves, devices which deliberately emit a certain amount of EM radiation on a given frequency. What were your observations, or do you have any, on the propensity of interference of wired devices, things which are emitting EM radiation not deliberately, but as a result of like a byproduct of the operation, such as, for example, a calculator emits a certain amount of EM radiation even though it's not a wireless device, just because of the way the circuits operate?
It's a very interesting question. Unfortunately, we haven't even looked at signatures of these devices. So I wish, that seems like a good thing we should work on next, because first thing we have to do is identify the device, and we have to build the signatures so that we can identify the device. If we can, that would be something we would love to study more. But we don't have an understanding of that at this point. Thanks.
Any other questions? Okay. Thanks very much.
Thank you.